Good afternoon, everybody, and welcome to today's presentation, Analytics 123, Ubiquitous Machine Learning at Scale. My name is Martin Willcox. I'm Teradata's Vice President of Technology for Europe, Middle East, and Africa. So I called this presentation Ubiquitous Machine Learning at Scale because I think a lot of commentators agree that we are on the cusp of an era of ubiquitous machine learning. And you won't need me to remind you that there's plenty of hype right now in our industry about machine learning. And if you're struggling to cut through that hype and understand what's real and what isn't and what all of this means, I highly recommend this book. This is a book by three economists, actually. They're economists, but they're also venture capitalists. So they have a lot of experience in working with machine learning and AI startups. And they have a pretty good sense of what works and also what doesn't work. And their central argument in prediction machines is that what we call AI today is really, for the most part, supervised machine learning and aimed at predicting events and outcomes. And that what recent advances in technology ultimately really mean is that we're able to apply supervised machine learning much more widely at much lower unit cost, and that even as the unit cost of making predictions is falling, the quality and the accuracy and the utility of those predictions is increasing very steeply. And because they're economists, they also point out that what economic theory tells us is that that means that machine learning will soon be everywhere. When the unit price of something falls very, very steeply, even as it becomes more useful and more usable, then typically what we get is more consumption of machine learning. As they put it themselves, cheap changes everything, and cheap means everywhere. One of their other central arguments in the book is that the chief complement to prediction is data, and that even as the algorithms that we used to train machine learning models become commoditized in some cases, the data that we use to train them becomes exponentially more valuable. And hold on to that thought, because it's something that we'll revisit later in this presentation. So ubiquitous machine learning essentially implies that machine learning will underpin all business processes and will help us to optimize all business processes. And as we seek to deploy machine learning more widely and to drive incremental improvements in some business processes where we've already been using machine learning, in some cases for a decade already, there are some really interesting things that we observe. And in particular, what we observe for a lot of industries and for a lot of use cases and scenarios, not all of them, but for a lot of industries and use cases, hyper-personalization, hyper-segmentation approaches are very, very relevant. And that means essentially creating very many models to predict individualized outcomes and the ability to score those models on an event-driven basis. So let's think about what that could mean for a typical organization. This is back of the envelope maths that we did with a large, well, I guess medium-sized to large European telco operator recently. If you start to think about hypersegmentation approaches to machine learning in mobile telecommunications, one of the obvious places to start is thinking about optimizing the network. So as we deploy 5G software configurable networks more widely, there's a need to reconfigure those networks on a continuous basis. Those cell towers are placed in unique locations. In some cases, they're deployed on different technologies. And if we want to predict utilization and interference patterns at the cell tower level, then that typically means one predictive model per cell tower. And those cell tower models may need to be scored multiple times per minute. So let's say we're scoring an individual model for a cell tower 10 times a minute. Multiply that by 67,000 cell towers, and that's 670,000 models a minute that we need to be scoring. If we think about hypersegmentation applied to customers and to customer journeys, then we're talking about creating individualized machine learning models to predict churn, propensity to buy, whether this is likely to be a fraudulent interaction or not. And obviously that means one model per customer. For this particular operator, that's 37 million models per use case, each of which need to be scored on an event-driven basis, so potentially multiple times per day. So ubiquitous machine learning in practice means millions of models trained on trillions of observations and scored in near real time. And hold that thought, because we'll return to it in just a moment as well. So where we're heading with machine learning, I think, is probably clear enough. The question we have to ask ourselves is, how are we doing? How are we getting on the journey to our destination? And unfortunately, I think you don't have to look very far for multiple data points that suggest that actually we're not doing as well as we would like to be doing. I think over the last couple of years, a lot of data scientists and machine learning engineers have established a way of working based on the creation of pipelines, typically end-to-end processes designed and intended to solve a particular business problem. And very often that pipeline starts with code for feature engineering. Feature engineering is obviously a critical part of the machine learning process. In general, if you have a choice between investing in feature engineering or investing in more sophisticated modeling techniques, in very many industries, very many scenarios, you get better return from better feature engineering. A simple model trained on well-engineered features often outperforms a more complex model trained on less good features. So feature engineering is obviously critical. But this approach of creating one machine learning pipeline for every predictive model that we want to create is leading to the emergence of what's often referred to as pipeline jungles in very many organizations. And that's a huge challenge because that creates a great deal of technical debt. And it also means very poor productivity and very long time to market, as the kind of numbers on this slide attest. So what we observe in the organizations that are more successful with machine learning than their peers is a different approach. If data scientist productivity is poor in many organizations today, and time to market for new analytics is often worse, we have to ask ourselves what's going wrong. And this pipeline per machine learning model approach means that we're often going all the way back to the data lake or all the way back to the source systems over and over again to capture more or less the same data, to create more or less the same features, even when we're building very similar models in adjacent spaces. And by contrast, best practice is increasingly to create an enterprise feature store, a repository of features with known, proven, predictive value that can be reused in multiple use cases and multiple scenarios. And where it's being deployed successfully, this approach is enabling leading organizations to dramatically improve time to market and data scientist productivity. Anecdotally, the organizations that are working this way also tell us that it's helping them to create better features, precisely because these features are being reused across multiple use cases, multiple scenarios, multiple models. If there are any issues with the features, they're actually identified more quickly than would otherwise be the case. So this is enabling us to build the right features, but also to build those features right. Now, if machine learning really is going to be ubiquitous, then it had better scale, and I mean really scale. So for example, sticking with the telecommunications industry, we work with one of the leading US mobile telco providers that has, I think they would claim with some justification, the lowest rates of churn of any mobile telco operator globally. When they create a new churn or a propensity model, they typically train those models on over 1 million observations, and they score them essentially on the entire adult population of the US, so 250 million observations. And they expect to be able to run 3 to 4 champion challenger iterations of model development alongside the same day. That's a great example of what Google a few years ago called the unreasonable effectiveness of data, of a relatively simple predictive model trained on a large number of high quality features, outperforming a more complex model trained on a smaller training data set. By contrast, in a lot of industries, in a lot of use cases, and a lot of scenarios, we see a different approach emerging. For example, in grocery retail, best practice for demand forecasting is increasingly not to create one predictive model per product or per category or for a group of stores and then to disaggregate that forecast across product lines. Best practice for demand forecasting in grocery retail is now to create one predictive model for each product store combination. So for a large EMEA grocery retailer with 50,000 SKUs in 3,000 stores, that's 150 million models that need to be scored and then trained at least once per day afterwards. Now, that's still a scale problem in the same way that training a model on 1 million observations and scoring a model on 250 million observations is a scale problem. But it's a different kind of scale problem because each of those individualized models tends to be trained on between 1,000 and 10,000 observations and scored on 10 to hundreds of observations of daily. And it's the amount of those models that we've got to train and score that gives us the scale challenge in that horizontal scaling approach. Ubiquitous machine learning is also a deployment problem because there is no return on investment until we're in production. So it becomes very important that we're thinking critically about what are the problems that we're trying to solve? Do we have the data available that will enable us to solve them? And then how can we take a model that's developed under laboratory conditions and ensure that it can be deployed at scale? And one of the key learnings, I think, of the last couple of years for a lot of organizations is that there is no single model training technology in particular to rule them all right now. We've been spoiled. Over the last couple of years, a number of really interesting technologies have emerged, each of which has a particular sweet spot. And trying to standardize throughout a very large and complex organization on a single model training technology is often very, very difficult. But where we're leveraging multiple different technologies to build models in the lab, very often we have a problem when we try and go to production, because very often getting to production starts with re-engineering and rewriting the model for a new technology, a technology that's supported in production, but not in our lab environment. And the way that we think we solve this problem as an industry is bring your own model scoring approaches by being open, particularly when it comes to the choice of model training technology, but by ensuring that models trained in those different technologies can be serialized and exported so they can be scored either centrally or on edge servers, but on a variety of different technologies. And if you have deployed or are deploying a data warehouse on a scalable high performance platform, then it's often a very logical place to build your feature store. It's where the data are after all. If it's also an active data warehouse that's connected to the operational touch points in your business, then it's very often a logical place to score those models as well, because it's where the data are and because it's connected to those operational touch points. So my coaching to business leaders is that they should start to think of machine learning in terms of 1, 2, 3. 1 is for data preparation and management. It's still the long pole in the tent. It still accounts for 80% of the cost, complexity, and effort of most machine learning products. And if we want to improve productivity, if we want to reduce time to market, and if we want to reduce technical debt, and technical debt is a drag on digital transformation objectives in very many organizations, then eliminating redundant data silos and the ETL and data pipeline processes that feed those redundant data silos is the way to do that. So best practice for the 1 in analytics 1, 2, 3 is to leverage data labs to support innovation, to leverage enterprise feature stores to support reuse of predictive features. The 3 in analytics 1, 2, 3 is for deployment and operationalization. There are several different analytic operationalization design patterns that make more or less sense depending on the use case. But in very many cases, scoring models in production and at scale requires us to bring together multiple data. And if we're bringing together multiple data, then the data warehouse is often a very logical place to score those models in production. Also critical to point out that the dirty little secret that we don't talk about in the industry is that model performance drifts almost as soon as we've deployed a model, particularly in adversarial situations. So instrumenting models to capture information about their performance is really, really important, even where we don't deploy them centrally. The 2 in analytics 1, 2, 3 is for model training. It's the sexy and the exciting bits, the bit that we all want to be involved in, and that's great. But it's important to realize that it's a relatively small part of the overall process. And it's really important to think critically about how the models we develop in innovation labs are actually going to be deployed in production. So this isn't a presentation about Teradata in particular. This is a presentation about what's going on in the industry and the approaches that are being leveraged by organizations that are successful with machine learning. But I did just want to point out that not all technologies are created equal from the perspective of being able to support machine learning at scale. And in particular, 6 of the things that we think are key are support for intelligent feature creation. I've mentioned a couple of times in this presentation that if you have a choice between a sophisticated model running on poor features or a relatively simple model running against high-performing features, 9 times out of 10, it's the relatively simple model created from sophisticated features that will outperform the more complicated model. So support for the hard work of feature engineering, for time series processing, geospatial processing, segmentation, binning, these kinds of block and tackle work is really, really important. Precisely because it's very difficult for organizations to standardize on a single technology for model training right now. We think in database support for R and Python is critical. And we touched earlier on the importance of bring your own model and analytic ops. We cannot restrict our data scientists to one particular model training technology. So we need to be able to import and score at scale models developed in a variety of different technologies, and also then to understand how those models are performing in production. High performance parallel processing is really, really important at the point that we want to score and train 150 million models a day. And particularly because event-based scoring is very important in very many industries. Logical hash-based indexes can be the difference between being able to score hundreds of millions of models in production or not. Last thing to point out, particularly if we want to leverage an enterprise feature store, we're supporting at least 2 fairly different types of workload: the model training workload and the model scoring workload. The model training workload is important, but typically not business critical in terms of its response times, whereas the model scoring workload absolutely is. So having sophisticated mixed workload management so that we can separate those 2 workloads and keep them apart is really, really important. This is a very brief survey of some of the recent projects that we've been involved in. Detecting and responding to remote account takeover fraud in retail finance requires response times measured in hundreds of milliseconds and a personalized approach, because we're comparing individual behavior during an online banking session with effectively a digital fingerprint. And building better cars by making welding robots smarter. Again, another hyper-segmentation, hyper-personalization approach, and the features that we create to support that use case are relevant across very many use cases and adjacent spaces. And optimizing call center usage with call deflection. Again, very many of the online banking variables that we use in fraud and other use cases turn out to have a high degree of reuse for this application. So in summary, think about ubiquitous machine learning as a data problem. Leverage data labs, leverage an enterprise feature store. Think about ubiquitous machine learning as a scale problem and have a strategy for how you're going to support both vertical and horizontal scaling of machine learning training and scoring workloads. And lastly, remember that there is no ROI until you're in production. So make sure that the platform that you're using to deploy your enterprise feature store can support both high performance model training, but critically high performance model scoring in production. Thank you very much indeed for your time and attention today. I hope you found this presentation useful. If you did, we are around for a longer discussion at 15:20 CET today. Thank you.